Go ahead.
Hi, okay. Yeah, so I'm Matt Heydeman. I'm a postdoc joint between the Institute for Advanced Study and Princeton University. And I'm going to talk about BPS black holes, microstates, and also some questions about whether there are gravitational observables that are integrable in a sense that I'll define to connect with the themes of this workshop. And I'd really like to thank the organizers for giving me a chance to speak here. Unfortunately, I'm obviously giving the talk remotely. It's still a bit of a busy time to be traveling. And it's currently getting close to 10 o'clock here on the East Coast time. So I will probably try to go through this talk fairly quickly, although there's a lot of material. It may be a little fast and I won't be able to do all the details I wanted to say. But if you guys like, I can stick around on the call for 10-15 minutes after the talk if people want to just discuss things. So maybe that will at least somewhat help with the online format. That being said, this talk is based on several papers with my co-authors here. And how about let's begin. So this talk is going to be a talk about quantum gravity. And so we know that quantum gravity is a big problem, and especially there are some questions about quantum gravity that we just don't have the answer to right now. So one question might be, for instance, can we compute the unitary collapse and evolution and evaporation of something like a Schwarzschild black hole and asymptotically four-dimensional Einstein gravity? This is not something that we, with the current technology, would really have any hope of doing. So I'm not going to try to address this question, but we're going to slowly retreat from these difficult questions and hopefully land on something that we can answer today in this talk. So maybe we don't know the full dynamics of a quantum black hole and the resolution of the singularity and the information paradox. These things might be still a little bit too hard, although some progress has been made in this direction. But maybe a slightly less ambitious goal would be to, for instance, compute, say, what I would call the exact density of states of a Schwarzschild black hole in some particular background or in some particular theory, which may or may not be that realistic. But even this, we essentially have right now no hope of doing it. And this picture is supposed to be a schematic picture for the density of states of some kind of quantum system. Maybe I would say that I want to find a density of states for something like a black hole. And if black holes are really quantum mechanical objects, which we would like to believe that black holes are ultimately ordinary quantum systems, this is at least the hope by many people working in this direction. If a black hole is an ordinary quantum system, I should have some set of microstates that if I sufficiently understood the theory, I could compute this density of states curve, and there would be some discrete set of states. But there is a question about the related to what I'll start introducing, this concept of integrability in gravity, or equivalently, will a black hole have some nice evenly spaced energy spectrum? We think that that is not true, and one can give fairly general arguments that the density of states of a black hole should essentially have very, very, very finely spaced microstates, so that this density of states almost becomes a continuum. And even more so, other arguments could tell you that essentially the spectrum of a black hole will, to very good approximation, look like the spectrum of a random Hamiltonian. Essentially, the degeneracies of a black hole are so large, and the dynamics of gravity and quantum gravity, even whatever that exactly means, are so complicated that in some sense, a black hole will look like a random matrix to some approximation. In a true theory of quantum gravity, there should be just one microphysical spectrum. Well, should be. I mean, this is at least an expectation if you believe black holes are ordinary quantum systems. All that being said, we still cannot really answer this question at this point. And part of the reason is that we believe that quantum gravity does have features of chaos and is explicitly not integrable. Quantum chaos, a quantum chaotic system would be perhaps one in which you have very densely spaced microstates, and we can only say things about the statistic average properties of them and of the microstates, and not the exact locations of all of them. So this is going to be part of the tension. And and why you might naively think that black holes are about the farthest thing from integrable. But this will be important when we talk about supersymmetric black holes. So I won't try to answer these questions, but I will try to answer the final point, which I will not cross out with this blue line, which is the goal today will be to compute some semi-universal features of the density of states of a black hole. And not just any black hole, but we'll be focusing on supersymmetric black holes for the following reason. Supersymmetric black holes have some, in particular, will have some exact set of degenerate states that can be computed at weak coupling with supersymmetry. Additionally, supersymmetric black holes are also ones that can arise in, say, the ADS-CFT correspondence, where we have some UV completion of quantum gravity that sort of flows to some Einstein-like theory in the infrared. And the black holes are solutions of this infrared theory, but in principle, they have a UV completion. And then finally, in the full string theory, in some cases, we can also make some exact counting of supersymmetric black holes. So you may already begin to be beginning to wonder what I mean when I say, on the one hand, I said that black holes are supposed to be like a random matrix. They're supposed to be extremely chaotic systems. But then on the other hand, I'm saying that using supersymmetry and ADS-CFT and string theory techniques, I can get some exact counts. And that sounds like it's contradictory. And part of the point of my talk will be to explain how these features, both of these features of sort of an integrable exact counting of the microstates, as well as a sort of quantum chaotic random matrix picture of the microstates, both can be true in some theories of quantum gravity that more or less come directly from string theory constructions. Are there any questions on this slide? It's sort of, we'll be setting the stage here for the rest of the talk. So if there are questions, let me know. If not, I'll keep going. Okay.
Are there good arguments that the spectrum would be discrete in some limit? I mean, inside of a black hole, you expect it's supposed to be just a singularity of the origin. So,
well, there's this. I think the argument is the arguments for why it should be discrete are well, there are quantitative arguments that you can find in papers, in particular some of the papers by Stanford and collaborators. But there's sort of the moral reason is that I could start with an ordinary quantum system that has some discrete set of states and collapse it into a black hole in some unitary way. And then that black hole, I ultimately would like to say that the black hole is also an ordinary quantum system. So if black holes don't ultimately have some discrete set of states, it may not be an ordinary quantum system. And when people, for instance, in three-dimensional gravity have attempted to compute, say, the density of states of the BTZ black hole, you would say, well, in 3 dimensions, there are no propagating gravitons. So maybe some of the problems of quantum gravity, the non-renormalizability, and so on in ADS3, so the BTZ black holes are ADS3 black holes. You might hope that so 3D gravity is solvable, but as Maloney, Witten, and many other authors later showed, the three-dimensional BTZ spectrum, it's both continuous and even worse, has some negativities where the density of states can go a little bit negative. So the argument why it should be discrete is because you'd like a black hole to be just like an ordinary quantum system. And we know that we can take an ordinary quantum system and collapse it into a black hole. So, this is not quite the information paradox. How does the information get out and so on and so forth? It's sort of an even more basic question is a black hole even an ordinary quantum system? I think if it doesn't have it ultimately in some UV description, if it doesn't ultimately have these features, then we sort of, either need to change quantum mechanics or a black hole behaves dramatically differently than what we might, expect from any other ordinary quantum system. So, yeah, I mean, the argument is essentially saying, either black holes are complete aberrations where the rules of quantum mechanics don't apply, or ultimately there is some UV description in which a black hole will look like an ordinary, if, perhaps highly chaotic, highly random, but ultimately just an ordinary quantum system. It's more aspirational. Of course, in certain cases in string theory, we can at least produce something that looks like a discrete set of states, at least for supersymmetric states. And and I'll be reviewing that part explicitly. So there's some hope from these other tools down here in this third line that this is indeed true. It doesn't have to be, but we'll try to evaluate to what extent we can make this work in quantum
Very
gravity.
good.
Yeah. So, is there any signature, at least, of these microstates using only the gravity path integral? And also, sort of, what is the role of the exact counting versus this expectation that they will look to very good approximation like a random matrix? Okay. So by quantum gravity here, I think probably most people would agree that string theory is essentially the only semi-working proposal of a theory of quantum gravity. But just because it works well doesn't mean we understand all the features of it, and especially these sort of black hole backgrounds where we don't really have control of the world sheet theory, it's a lot less clear what's going on. So by quantum gravity here, I'm actually going to mean the Euclidean gravitational path integral. Now, ultimately, maybe this object doesn't exist in string theory, but we have reasons to think that it's at least a good approximation to what's going on at long distances. So, of course, we start before we even talk about the path integral, we can talk about the Bekenstein-Hawking formula, which says that a black hole has an entropy that goes like the area. Of course, this formula has h bar, but the problem with the Bekenstein-Hawking formula is that it's sort of just a prescription. It's just a guess based on general argument. It's not, you have to do a bit more work to actually compute this in some theory. So a slightly better prescription is this Gibbons-Hawking prescription, which will be that for instance, we want to compute a gravitational partition function, which may depend on some boundary data. So we might compute the partition function of a theory on some manifold or on a theory which has some boundary conditions. So in this talk, I'll be considering, again, Euclidean gravitational path integrals on a manifold which has a boundary of length beta. So beta will be the inverse temperature, the inverse Hawking temperature of the black hole. So the partition function depends explicitly on beta and possibly other chemical potentials. And the idea will be that in gravity and in Feynman's path integral applied to gravity, we should sum over all manifolds that have the same boundary conditions and weight them by their Euclidean action. That would essentially be a sort of a saddle point approximation to the gravitational partition function. So the idea is that we sum over solutions, we weight them by their classical action, as well as the one loop determinants. So this procedure is sort of a genuinely better, more quantum version of Bekenstein-Hawking, because in principle, you can compute these various things. Of course, the problem is that we don't really know what the integral of a metric should mean in any examples above essentially 2 dimensions. As I mentioned, even 3Ds is a little bit tough. So it's not really clear, for instance, what saddles contribute. It's not clear what we should include in this sum. We may not be, these one loop determinants might not be well posed, or they might be divergent and so on and so forth. Maybe we can't just have a gravitational path integral, that maybe we need to include other UV ingredients, such as things coming from string theory. So why talk about this gravitational path integral if, this kind of formula was written down by Gibbons and Hawking and others 50 years ago now, or something like that. So why are we sort of revisiting it with more energy in recent times? Well, the idea is that string theory does, in principle, provide a UV completion of what this Z should be. And there's also, in string theory, in some cases, there'll be candidate microstates for the black hole. And even better, when we put this black hole in ADS and do ADS CFT, we can sometimes precisely match certain protected quantities, as I said, the supersymmetric quantities, between a Euclidean gravity answer and a dual boundary CFT, where I'm just doing a path integral of an ordinary quantum system. So especially in ADS CFT, black holes, at least there's a good argument that black holes should be like ordinary quantum systems, because in some dual variables, it's just something happening in the CFT. It might be a very complicated sector of the dual CFT. So that makes it hard to study, but at least in principle, we've recast the black hole as an ordinary quantum system. But ultimately, Euclidean gravity seems to get you the right answers, even if we don't know yet exactly why. So, the next point I want to raise is I keep mentioning that we can make exact counts. And so an example, for instance, is the famous Maldaceni's famous original duality, which says that this large n SUN at 40 n equals 4 Supergavity Mills theory will be dual to ADS5 cross S5. And if you just have empty ADS, for instance, we can compute certain observables as anomalous dimensions and things like that can be exactly computed using integrability techniques in the sense of the world sheet theory, or the spin chain of the spin chain description of the single trace operators of the dual n equals 4 theory. So this is a case where we have some, using ADS-CFT and large N, we have some exact calculations, usually for perturbative fluctuations around empty ADS. Whereas a black hole is a big, heavy thing that backreacts on the geometry by a large amount, and some of the integrability techniques would not seem to apply here. So I should point out that along these lines, at least in three-dimensional gravity, there's a recent paper by Edward Witten and mathematician Schlenker, who essentially in the context of three-dimensional gravity, they were looking at essentially gravitational partition functions, these Z on general hyperbolic three manifolds. And they argued that if you are looking at some observable that's below the black hole threshold, so the energy of a state passing through some cycle of a Handel body is below the threshold energy to make a black hole, then there should be, at least in some dual CFT, some integrable technique to compute the observable exactly at large N, and then with a power series expansion to correct that. However, they argued that above the threshold, and this is perhaps more of a conjecture, but I think it's an interesting one, that above the threshold to produce black holes, a lot of observables, if I just try to do semi-classical gravity, some observables will appear to be either averaged or subject to quantum chaos and so on and so forth. So the idea is that somehow gravity will work very well as long as I'm not in the black hole regime, and or rather, gravity will look like an ordinary quantum system as long as I'm below the black hole regime, but above it, gravity will give only some sort of averaged answers. That was their conjecture. So as I've already said and emphasized, so there's fairly general arguments that say that black holes should have features of quantum chaos and random matrix theory. And I would refer people to the work of Saad Shanker in Stanford, for instance, which probably is known to many people in the audience, for a very explicit example where a quantum gravity theory appears to give averaged answers that essentially agree with the spectrum of a random matrix. So some observables appear to be computable using some exact integrability techniques in ADS-CFT, and some appear to not, or it's hard to compute them exactly, but you can compute sort of random or average properties about them. And the key is the black holes, and especially black holes which develop an ADS2 throw. So on the flip side, there is some apparent exception to this non-integrability of gravitational observables. And for instance, in n=4 super-Yang-Mills, we can look at 1/16 BPS states of this superconformal field theory. And so these 1/16 BPS states, among them, a large number of them are essentially dual to supersymmetric black holes inside ADS5 cross S5, the Glukhovsky-Rial black hole. And I'm going to say some general things about what we did, but eventually I will come back to this example and explain, hopefully somewhat clearly, this story in a little bit more detail than what we had to add to it. But so as in the first slide, I could try to compute Z of beta as a function of some inverse Hawking temperature, as well as some chemical potentials, because of course n=4 has global symmetries and rotational symmetries, so I can introduce chemical potentials for them. And then the partition function of n=4 on a thermal manifold, S1 cross S3, is going to be some trace over the Hilbert space, weighted in usual statistical mechanics in the grand canonical ensemble by some chemical potentials and charges in this way. Now, if I take a particular refinement of this partition function, which is this would be hopeless to compute in a strongly coupled gauge theory, but if I choose some combination of chemical potentials and tune them to some value, that will be equivalent to inserting -1 to the F in the partition function. And as shown by Witten and later Maldacena and his collaborators, whose names will appear in a moment, this object here is essentially a superconformal index of n=4 super-Yang-Mills. It's independent of the temperature, and also independent of the couplings of the gauge theory. And this index can be computed exactly in n=4 super-Yang-Mills. Now, it was shown more recently, so there were some original works quite a while ago. They weren't able to quite get the black hole entropy due to some technical issues, which, well, you'll have to read the recent papers to explain why they didn't quite get it right. But then there was a much renewed interest due to the work of a large number of authors who had supplied a partial list here to ultimately show that this superconformal index at large n in n=4 super-Yang-Mills, which is, again, it's a refined partition function in some sense. This superconformal index when I take the logarithm, it exactly matches the action of the supersymmetric black hole in the dual ADS side. So this is an observable that you compute in free theory in n equals 4 superunion mills, and you can map it to the known gravity solution on the bulk side. So because you could compute the index just in the free theory, there's a sense in which this is an integral model because I am doing a free theory calculation, but it can be mapped to some, very non-trivial soliton in the supergravity bulk. So on the one hand, I said gravity should have some averaging, there should be some quantum chaos, and it's hard to resolve individual microstates, but this superconformal index appropriately computed will end up coming out to be an integer in some cases where you can do the calculation carefully. And so this sounds like some integrable sector, and it sounds like it's in contrast to the chaos, the quantum chaos I talked about before. So in order to sort of explain how we can have our cake and eat it too, in the sense that there are exact microstates that we can see either in gravity or in the field theory side, but also these black holes have a sort of chaos sector, I need to review some general things about black holes, and in particular, what happens when a black hole approaches extremality and develops a long ADS2 near horizon region. So the key to my story today will be the importance of the ADS2 region, which is found for extremal black holes. So the idea will be that I'll consider some asymptotically ADSP cross SQ or flat space black holes. There'll again be some Euclidean thermal time, which will be this circle here. And then there may be some, so there'll be some ADS2 geometry, which I'll draw sometimes as a funnel or as a hyperbolic disk. And that's the near horizon region of an extremal black hole. There'll also be some squashed spherical horizon. So the internal manifold will depend on the problem we're considering. I'll give some explicit examples in a moment. So the idea is that when I have some charge and rotation for this black hole, we can have a very large, macroscopic, classical looking, an enormous black hole that still has its Hawking temperature going to 0 because of the way the extremal limit works. Now, the idea is that if I have a very small Hawking temperature away from 0, I can compute in semi-classical sort of Gibbons-Hawking style or semi-classical black hole thermodynamics, I can compute the energy and the entropy as a function of the temperature as I tune the temperature away from the exact extremal value. So there's some exact E0 and S naught, which will be the extremal values, and then there'll be some characteristic scale times for the energy will grow quadratically with T, the entropy will grow linearly with T. So this is just semi-classical black hole thermodynamics as I try to move a little bit away from the extremal limit. Because again, from arguments that I have sort of said in words, but not reviewed in technical detail, the problem comes from the sort of near horizon region of the black hole, whether I have it in flat space or not. So the near horizon region of a near extremal black hole. So the problem with these formulas, that they're nice black hole thermodynamics formulas, and this is sort of what you would naively get, but the problem with this is that essentially, given by this old paper by Presley, Schwartz, Shapiro, Trivedi, and Wilczek, the idea is that if you look at the energy of a single Hawking quanta, for instance, will have an expected energy of order T. But the energy close to extremality grows like order T squared. So at sufficiently low temperatures, there will be a point where the black hole is trying to emit a Hawking quanta of energy of order T, but emitting a T, essentially, roughly speaking, T squared is smaller than T for sufficiently small T. So the idea is that a single Hawking quanta will change the black hole's energy by an order 1 amount when I'm very close to extremality. So this assumption of the semi-classical black hole thermodynamics will actually break down. And whenever you have a breakdown of a semi-classical thermo, it just means that we should replace the thermodynamics with some quantum statistical mechanics. And of course, that gets back to the original problem then, how do we treat the black hole as a quantum system? But here it's particularly sharp because, as the temperature gets lower and lower and lower, the classical thermodynamics just gets worse and worse and worse. So we have to figure out what's the correct quantum description of the black hole. There's another thing, which is that yes.
What's M gap?
Yeah, so M gap is some kind of characteristic energy scale. It'll end up being, roughly speaking, the specific heat of the black hole, but it's something you can compute knowing the black hole solution. You sort of plug the black hole, evaluate the action of the black hole, and then compute the partition function by saddle point, and you can extract the energy and entropy, Taylor expand at small temperatures, and MGAP will just depend on the charges and the mass of the charge parameters and the mass parameters and the rotations and so on of the black hole solution. So black hole solution will have some numbers that parameterize the solution, and this will be some function of those. I'm not giving it because it's some complicated rational function, but it's something that's completely ordinary and just comes from doing a Taylor expansion once you know the black hole solution and its action. Yeah, so from an ADS-CFT perspective, the ADS2 region, this sort of throat region, is too trivial. Essentially, if I try to turn on finite energy excitations in ADS2 or try to create Hawking quanta in the near horizon region, the back reaction on the geometry will be very large, and you'll actually destroy the ADS2 region. This is sort of dual to the statement that a one-dimensional conformal field theory, a CFT1, will only have ground states, sort of because the stress tensor vanishes for a CFT1, the Hamiltonian vanishes, and you only have ground states. So it seems hard to have essentially any kind of dynamics in ADS2 region. This is again for exact ADS2, but as long as the temperature is non-zero, the black hole solution is never quite ADS2. The throat gets very, very long, but there's always ultimately an asymptotic region. So the fix for these problems will of course be to turn on a finite temperature and then do the gravitational calculation more carefully. There appears to be some audio back reaction as well. I'll continue. Oh, okay. Okay. So in a little bit more detail, what goes wrong in ADS2? I guess I said this before, and I'm running a little behind, so let me go quickly. So Hawking's calculation essentially fails at low temperatures, and so it must be replaced by some proper quantum statistical mechanics. And as I said, it's also hard to incorporate excitations, back reaction, and boundary gravitons. So this pure ADS2 holography seems different than other examples. So the fix will be, as I said, to turn on finite temperature and compute the gravitational path integral as a function of a non-zero temperature. So the idea will be that exactly zero temperature, the near horizon region of the black hole in the sort of RT plane, the radial and time directions, will be this Euclidean disk. So I took that cigar picture and I just smushed it down to the plane, and there'll be a hyperbolic exact ADS2 metric there. But at finite temperature, I don't have exact ADS2. In some sense, I am cutting off the ADS2 at some radius, and this is where the ADS2 will be glued to the higher dimensional geometry that might be asymptotic flat space or asymptotic ADS. But the idea is that once I turn on finite temperature and introduce this sort of cutoff surface, I want to do a gravitational path integral. So I want to sum over all geometries that have the same boundary conditions. And the natural boundary condition that I fixed is the total length of the boundary, which is just the inverse temperature, which I'm taking to be not infinite. Where, here this picture is supposed to mean the length of the boundary is infinite. Here it's supposed to be some finite curve. But of course, there are other manifolds that everywhere look like ADS2, but the curve, the choice of the cutoff surface will be different than sort of this choice that I drew arbitrarily. So the idea will be that in a gravitational path integral, I really should sum over all geometries that are locally ADS2, which is what at low temperatures, that's what the black hole solution is localizing to these ADS2 solutions. But because I have finite temperature, I can allow sort of wiggly boundaries, as people will say. And the idea is I should somehow sum over all geometries that have the same length of this wiggly curve, but the shape will be different. And this will be at least some, this gives you some idea of what I mean to do a gravitational path integral in this setting. I mean to sum over all geometries that have the same boundary conditions and are locally look the same, but they might be globally different because their shape of their boundary is different. Are there any questions on that? This is something that maybe some people in the audience know very, very well, perhaps even better than me. That's likely. But maybe some people haven't seen this idea before. This picture was sort of advocated by Maldacena, Stanford, Yang, and also Alexei Kitaev in his work on two-dimensional gravity in the SYK model. So are there questions on this picture, or should I move on?
Well, a little bit, because you're saying you're patching together a black hole to an external geometry.
That's right. That's right.
Classically, is that stable? You know, that's stable classically?
Yeah. So
or maybe it's not.
the patching is an artifact of how I'm doing the calculation. The idea is that, way out here in this funnel picture, I just have ordinary flat space and there's nothing quantum happening. There's no strong back reaction. It's just a GR solution that I treat completely classically far away. Whoops, sorry. But the idea is that really, really close to the horizon, there's a very long throat, and whatever is happening way down here deep in the throat basically can't talk to the outside region. So in the limit where the temperature goes to infinity, this throat goes, temperature goes to 0, this throat becomes infinite. But if it's finite, I can again cap it off. I can draw a Euclidean cigar cap right here. The idea is that I can cut off the geometry at some arbitrary curve. And as long as the temperature is low enough, so basically sufficiently low temperatures, this arbitrary curve, the position of it doesn't quite matter. So the idea is that I should have drawn a little red wiggly curve here, because imagine I've drawn a red wiggly curve here, which is matching this kind of red wiggly curve here. The idea is that outside, away from this red wiggly curve, the geometry is very, very weakly curved and not quantum. I treat that part classically. I then say, take my boundary conditions at infinity, propagate them to the location of the cutout surface, and then cut off the geometry, then do a path integral in this near horizon region. So essentially, it's saying that quantum effects become important very close to the horizon of a black hole at low temperatures, but classically, but far away, quantum effects are not important. So I just treat those classically. The point here is I'm looking for a way to get this extremal black hole to degenerate into a two-dimensional gravity problem, which I then can solve.
I have one question.
Mm-hmm.
So for the extremal black hole, so according to your explanation, there is no way of deforming the geometry satisfying the boundary condition. Is that what you are saying or implying?
I think what I'm saying is that if you try to just take rigid ADS2 and put some matter or dynamics in a exactly 0 temperature rigid ADS2, that destroys the ADS2 solution. Essentially, in two-dimensional gravity, turning on any stress tensor usually causes things to blow up and destroys the asymptotics. But the point is that if I'm not in exact ADS2 gravity, but I'm in some limit where far away my solution is some higher dimensional flat or ADS space, and then it's only in very close to the black hole that anything quantum mechanically interesting is happening. The point is that I can allow a very small amount of back reaction, but the back reaction will end up being contained entirely in the wiggly boundary, how I've glued it to the asymptotic region. So
I understood. Okay, thank you.
Yeah, small back reaction that ends up being sort of almost trivial, but not completely trivial. And it will end up fixing these problems that I've mentioned here. So, okay, so this is a story that many other people have given talks about long before I was interested in the subject. The reason why I'm giving this review, because some people haven't seen it, the idea is that I'm going to apply this idea to supersymmetric black holes where we have independent checks that this prescription might make some sense. And we'll ultimately compare with some predictions from string theory and ADS-CFT. So in the non-supersymmetric case, you can do this and you get some answers that actually, well, I'll explain later on in the talk. So roughly speaking, what happens by doing this procedure is that the higher dimensional black hole reduces to a two-dimensional gravity problem. And a two-dimensional gravity problem where I somehow have to sum up a bunch of geometries that all locally look like ADS2, but globally their boundary conditions are different. Sort of I'm summing over all the possible geometries that I'm gluing to the asymptotic region. Now, this prescription, maybe some of the words sound nice, but does it actually make sense to do this? As usual in gravity, we don't really know what the rules are. So the real big development that got lots of people interested in this kind of idea came from Kitaev, because what Kitaev did was he tried to find some kind of model that was dual to this ADS2 part of the problem. So he wasn't thinking about the higher dimensional black hole picture. He was just thinking about a toy model of two-dimensional gravity, which is Jakob-Teitelbaum gravity. And he found some model that had the same spectrum as the JT gravity. So yeah, time is going a little faster than I was expecting. So, okay, let me review this super quickly. Again, it's something that I think maybe many people have seen. So the modern perspective is that this inconsistency of ADS2 holography and this sort of CFT1 being too trivial means we should better understand this SL2R symmetry that acts as the isometries of the ADS2 region. So Kataev essentially showed that this earlier model by Sachdev and Yi had some very interesting holographic features. So this is a one-dimensional quantum mechanical model. And I will build quickly the dictionary between field theory and gravity on both sides. So this is a one-dimensional quantum mechanical model with a large number of fermions. It's a large N system that has an exact large N solution. And the equations that determine the large N solution of this theory actually have a reparameterization symmetry. And the dual statement on the gravity side is that whatever this large N quantum mechanics theory is, it's supposed to be dual to some kind of gravitational system that has an ADS2 vacuum, and the diffeomorphism symmetry is sort of dual to this reparameterization symmetry. Now, the idea is that when I turn on finite temperature, I actually break the reparameterization symmetry down to a subgroup. And that's a little bit like saying that I pick an ADS vacuum, which has an SL2R isometry and not the full diff symmetry. Now, finite temperature is what breaks the SL2R. And on the gravity side, the finite temperature is what is sort of deforming the ADS boundary. So just to quickly go back, sort of this is the exact ADS2. When I turn on finite temperature, that means the length of this curve is finite, but also there are other geometries that have a finite length of this boundary curve as well. So the finite temperature is breaking this SL2R explicitly. And I've now explicitly broken a symmetry, and I want to ask, what is the action of the modes? So there were some zero modes, which corresponded to these reparameterizations. When I break a symmetry, they're no longer zero modes. What is the effective action of the zero modes? And in the field theory side, one finds this Schwarzian effective field theory. So this is some quantum mechanical system, has a large N solution. When I compute partition functions at finite temperature and ask what is the the mode that dominates the physics of this quantum mechanical model, I'll find something called the Schwarzian EFT, and I'll write that down in a second. Now, on the gravity side, when I ask what is the effective action for this ADS2 JT gravity theory, the JT gravity theory is essentially a topological theory. I integrate out the bulk, and the only thing that remains is an action of the boundary mode, and essentially the Gibbons-Hawking-York boundary term of the gravity theory will become the Schwarzian derivative. So this is sort of the dictionary. Now, SYK model is not exactly an ordinary quantum system, and it's not exactly dual to Einstein gravity, but the point is that it's a solvable system. It's sort of, in some sense, an exactly solvable system that has a very interesting effective field theory, which can be matched to the action of this wiggly boundary curve. So it's hard to sort of directly build SYK into some UV setup, but this Schwarzian physics appears universal. Okay, so that's my setup. Now, what we did was we took these ideas for this just pure JT gravity, and we generalized them to a bunch of supersymmetric black holes where, again, independent things were known. Some of these black holes have been studied for over 20 years in string theory. And what we did was we turned on finite temperature effects for these supersymmetric black holes, and we computed the generalization of the Schwarzian and solved these theories exactly. So we can now, what I'll write is that the Lagrangian density of this effective boundary mode is this Schwarzian derivative, which is familiar from two-dimensional conformal field theory, but it's kind of a crazy combination of derivatives. It's not at all, it doesn't at all look like anything that would give you a sensible Lagrangian. But the action is just, again, so this is the action of the boundary curve and gravity side, and on the quantum field theory side, it's the action of the emergent broken symmetry mode coming from this large N model. So this is the action. Now, if we have some higher dimensional black hole that has some internal manifold, like some spheres, say a BTZ will have an internal S1, or a black hole in flat space will have some two-sphere that describes the horizon topology. In addition to the Schwarzian derivative for this boundary mode, I might also have, say, a particle moving on a group manifold that parameterizes not just the reparameterizations of the boundary, but the reparameterizations of the internal manifold. So I'll have the Schwarzian plus some other compact space, so some particle moving on a compact space. So now this coupling constant M gap that was asked about before, this is essentially the scale where the black hole thermodynamics broke down, and this is the coefficient of the Schwarzian action. So what I'm saying is that this higher dimensional quantum gravity problem I don't know how to do. At low enough temperatures, it reduces to a sort of two-dimensional problem, which can be integrated out into a one-dimensional quantum mechanical model. And this Schwarzian action controls the first correction of the first finite temperature correction to the extremal answer. So the idea is that my system, the entropy will be computed by the extremal entropy plus whatever I get by quantizing the Schwarzian derivative, and the coefficient turns out to be exactly the same. So this Schwarzian derivative is, as has been argued by people down here and in other places, this Schwarzian derivative controls the response of the extremal black hole to a small finite temperature. And its physical origin is the fact that the boundary conditions, the boundary of the ADS2 space can wiggle in some sense. And I need to sum over all such wiggles. So by following this logic, we can construct a family of Schwarzians with different amounts of supersymmetry, 0, 1, 2, 4, and sort of more generally adding external group symmetries to it. And they'll always, for any Schwarzian that we find here, this always corresponds to the breaking of some superconformal algebra, conformal or superconformal algebra by finite temperature. And then there are different black holes that realize this. The gap I'll come back to in a second. I won't explain this yet. So the idea is that we were able to test this in lots of examples, and as we increase the amount of supersymmetry, we find much more complicated super Schwarzian. The largest one we were able to find was the n=4 super Schwarzian, which essentially involves, let me not click all the way back, but it's now, in addition to the wiggly bosonic reparameterizations of the boundary curve, there are now n=4 super reparameterizations. So fermions and also vectors, not vectors, but particle moving on a group manifold here. So this is what we did. I think I'm about halfway through the talk, but I'm so let me skip the details of the super Schwarzian. The miracle, I'll say without explaining any of the formulas, the miracle of this crazy Schwarzian derivative theory is that even though it looks highly nonlinear, and I should think of, I'm doing a path integral over all possible f's here, and the f's are all possible shapes of this wiggly curve. So even though this theory looks horribly nonlinear and complicated, it turns out that the partition function of the Schwarzian theory can be computed exactly by localization. And here I don't mean supersymmetric localization, but I mean an honest Duistemont-Heckman or Duistemont-Heckman type localization, because essentially the path integral over these boundary wiggles is an integral over a symplectic manifold with a U1 action. So these Schwarzian partition functions can actually be computed exactly. Now it's quite complicated. And for instance, for n=2 super Schwarzian, the partition function will depend on the inverse temperature and some chemical potential alpha. And this is the exact partition function that one gets by quantizing this. It'll end up being a Schwarzian plus a scalar mode plus some fermions that I didn't write. So I'm skipping all details, but it's kind of a miracle that these theories are exactly solvable despite being very nonlinear. So this is sort of how we've been able to get some answers about the higher dimensional black holes, is that at low temperatures, they'll degenerate into a two-dimensional gravity problem, and that two-dimensional gravity problem itself is equivalent to a sort of one-dimensional quantum mechanics that we can solve exactly using localization. Are there any questions about this? I'm going to just race through the rest of the examples now. Questions about this? I'll explain all the parameters later when we get to an example that people are familiar with. So as I said, Kataev started with the SYK model, and he argued that this was dual to some JT gravity. You can also write down some extended SYK models, extended supersymmetric SYK models. And these are, again, models of random fermions and that have, in the infrared, the theory will have, at zero temperature, will have these supersymmetric reparameterizations. And the Schwarzian mode that you can derive from this n=2 SYK will be a theory of n=2 super reparameterizations. So this was a model that was worked up by Fu, Magayoto, Modelsane, and Sachdev. And in one of our recent papers, we spelled out a lot of the details of this model. and we computed various quantities like the extremal entropy and the density of states and various things like that as a function of arbitrary chemical potentials. And one can also compute things like the superconformal index. Because this theory has n equals 2 supersymmetry, there's actually a large set of BPS states. Similar to the index that I mentioned for n equals 4 super Yang-Mills, this is sort of a toy quantum mechanics problem that one can also evaluate the index and ultimately match it to some kind of gravity model. We also found some generalizations of n equals 2 SYK that have a more interesting spectrum. And actually the model that we found in the infrared, the spectrum that you get will end up having exactly the same shape as the analogous problem in n equals 4 super Yang-Mills. So let me come to that in a second. So just to recap, we essentially checked a bunch of examples which involve reducing higher dimensional black holes down to a two-dimensional effective field theory that can be solved exactly. So this is a gravitational EFT that preserves various amounts of supersymmetry, and all kinds of different black hole examples will land you on this two-dimensional gravity that we can solve exactly. So for instance, four-dimensional flat space black holes, extremal Reissner-Nordstrom. We can also do the 4,4 BTZ black hole, which is sort of dual to the D1, D5 system, and also ADS5 cross S5 black holes, which I'll cover in the remaining, I'm going to say 10 or 15 minutes of my talk. Is lunch right after this, or?
We have no problem, right? No problem. So,
yeah, I started a little bit late, and I might go a little over time, but I'll try to wrap it up and save more time for discussion. So I'll explain what the actual spectrum of these models is in a second, but I deliberately left the plot for the end, so it's more of a discussion feature. So we can check lots of different examples, and these are rather technical. We're doing sort of a supergravity reduction down to 2 dimensions, and then sort of the boundary mode is a very complicated supersymmetric extension of the Schwarzian theory. So this was very technical, but we get very nice answers at the end that we can compare with other essentially other predictions from ADS-CFT. So let me just go through this ADS5 cross S5 example quickly. And so essentially we have black holes inside ADS5 cross S5. This will be something like the Gokowski-Rial black hole. And schematically, when I put a black hole in ADS5 and I go to the near horizon region, I'll again have some long ADS2 type throat, which I will never take it to be exactly extremal. The idea will always be that I've cut out some ADS2 region and I imagine gluing it to the rest of the ADS space. And then the horizon will have the topology of an S3 cross an S5. But for the experts in the audience, they know that these black holes have to rotate, and actually these, to preserve supersymmetry, these black holes will have to rotate. In fact, they sort of rotate on the S5 and on the S3. So the geometry is not ADS2 cross S3 cross S5, but it's really some kind of complicated fibration. I'll write the metric in a bit. So we're going to fix some charges and fix some potentials. These will be the boundary conditions. We compute the partition function with these choices. We will not include the Kaluza-Klein modes. This will be the sort of the Kaluza-Klein modes, and the one-loop determinants of matter fields will be similar to things that Sen computed. So I'm focusing on the low temperature corrections, and we're not going to include wormhole topologies or D-branes or orbital folds. Of course, those things would be interesting to include and probably change the answers. You can think of this as being sort of the leading order quantum correction to the black hole entropy at sufficiently low temperatures. So the theory that we're looking at can be exactly solved, but it only gives the first term of the low temperature corrections to the partition function. So, okay, we start with a 10-dimensional type 2B. We have this Gokowski-Rial solution. We essentially do a Kaluza-Klein for technical reasons. With Kaluza-Klein, reduce this theory down to 5 dimensions. So there's a metric and a 5 form. These are the only fields that we turn on in 10 dimensions. And this dimensional reduction gives you this 5-dimensional minimal gauge supergravity. So G5 will be essentially 1 over n squared, where n is the SUN of n equals 4 super Yang-Mills. So we'll write lots of formulas with G5, and just think of 1 over G5 as being like n squared. And when gravity is a good approximation, n is very large. So we'll see that essentially all charges will be of order n squared, for instance. So this is the black hole solution. This was found in some form or another by Gokowski-Rial and explored in quite a bit more detail by CCLP. And so I wrote this more just to give you a picture of what the solution is. If you worked on this, then you know that you know about this, and if you haven't, then this thing just looks like a mess. So I mostly display just to show that there really is a gravity solution here that when I tune various values of these parameters, this thing will actually become a supersymmetric black hole. But the point is that the formula that I've written here is valid for sort of any set of charges and any temperature. So this is the full solution and not necessarily the one in the extremal regime. But at some ADS Kerr-Newman, there are 4 parameters. And this black hole, the claim is that it's dual to states in n equals 4 super Young-Mills with some scaling dimension, R charge, and spins that are set by roughly these parameters here. Okay, so this looks like a mess, but you can do it very explicitly. That's what's nice. So because I'm doing grand canonical ensemble, I have to make sure that there's a chemical potential for the electric field. This is a charged black hole, so there's a gauge field. There will also be some rotation, so these be some angular velocities, omega-1 and omega-2, and delta R will tell me where the position of the Euclidean horizon. So, okay. So in the grand canonical ensemble, the idea will be I want to do the gravitational path integral, and the first step is to evaluate the saddle point evaluation, which means take E to the action in the grand canonical ensemble. Of course, there may be other saddles, and actually we'll explicitly include other saddles in a second. For instance, there's also a saddle, depending on what the boundary conditions are, there could be a saddle where thermal ADS without the black hole contributes. So the idea is that we want to compute this partition function in an ensemble where the dominant contribution is this long ADS2 throat geometry and not some other geometry. So that's a technical point that I'll gloss over it, but we were careful in doing that. So you can evaluate the on-shell action of this theory, including the given Hawking-York term and the holographic counter terms. And you can evaluate the Bekenstein-Hawking entropy. Again, these are all semi-classical things. And this will finally, you can put everything together into some quantum statistical relation, which says that the on-shell action of the black hole is essentially the grand canonical action. This is sort of a restatement that black hole thermodynamics is supposed to work, at least semi-classically. Okay, so, okay. We can take various limits of the solution. As I said, this is a solution that in general is not supersymmetric and not extremal. So depending on whether Q and M and the rotational parameters satisfy this relation or they don't satisfy this relation, and also depending on whether the Hawking temperature is greater than 0 or equal to 0, there's a priori different things. So there's the generic black hole, which is just the metric I gave before. When I tune the temperature to 0, this will be an extremal black hole that's not supersymmetric. Of course, if I have a black hole that's exactly 0 temperature and satisfies this supersymmetric relation, that will be a BPS black hole. And sometimes I'll put stars to note BPS. Now, it turns out that the intersection of the 0 temperature surface and the supersymmetric surface is equivalent to a funny nonlinear constraint. And this is very hard to see in field theory, but this is something that's sort of forced on you by gravity. The last corner of the column is a little bit unusual. It turns out that in Lorentzian signature, these black holes have closed time-like curves. It's like you tried to make a supersymmetric black hole that was still finite temperature, and that's a little bit paradoxical. So if you write down a solution that has T greater than 0 and this BPS relation saturated, the black hole will have closed time-like curves, so we'll forget about them for now. But there's some work in progress to try to make sense of these guys as well, even though they're sick in Lorentzian signature. So in any event, essentially we want to try to approach this BPS surface. The idea is that we're going to tune the black hole parameters so that this quantity is getting close to being saturated and the temperature is getting close to 0. And that will be a near BPS black hole, which we've shown in previous papers is controlled by this supersymmetric Schwarzian theory. So just putting it together, we want to compute a partition function. Partition function is like a trace. We don't know how to do trace in quantum gravity, right? Because we don't know what the Hilbert space is. So the idea is that we want to compute this trace, and in n equals 4 super Young-Mills on the dual side, this trace makes sense, but in gravity, we don't know how to do it. But let's say that there was a way to write this formula in gravity, then immediately the trace, because of the E to the chemical potentials, this will be invariant under some imaginary shifts. So the idea is that when we rewrite the trace as a sum over saddles, remember the first slide where I say that Z really should be traced over the Hilbert space, but in the sort of semi-classical saddle point approximation, Z will be some sum over saddles, where I take the E to the grand canonical action and then weight it with the one loop determinant. The idea is that this trace is invariant under shifts of these chemical potentials. And so I should really sum over all these possible integer shifts when I write the trace as a sum over saddles. And this was argued in this paper and in other papers as well. I don't have time to completely explain why this is, But the idea is that these different solutions, these different saddles with different integer shifts correspond to different gauge bundles of the this S3 cross S5 geometry fibered over the ADS2. So the idea is I have to sum over all these 10-dimensional gauge bundles, which are labeled by integers. So this is a technical point, but it's important because there's going to be a sum over integers showing up. I wanted to explain that these are honest sort of gravitational solutions that satisfy the same boundary conditions, but have different action in general. So we sum over all flux sectors, which is, again, exactly what you would have to do in n=4 super Yang mills if you would try to interpret this as a field theory formula. So, okay, some technical points aside, we have to change ensembles. We have to define some reduced chemical potentials. This slide's a little bit of a mess, but let's just stare at the final answer, which is when we pick an appropriate ensemble in which these near BPS black holes give the dominant contribution, the partition function in this approximation will be given by a sum over a single integer of e to some, what I call mixed ensemble action, again, weighted by one loop determinants. So we massage the formula, the general formula, down to a form where it can be compared with the two-dimensional gravity answer. Yeah, this is where the sort of the one loop corrections are easiest to compute. This I mixed ensemble is just a classical action. So the one loop corrections are the only things that we need, and these are given precisely by the Schwarzian mode. So, okay, so the idea is that to figure out what Schwarzian it is, we need to just look at the symmetries of the problem, because the idea is that the Schwarzian is the effective action for the breaking of the symmetries at extremality. We turn on a finite temperature, we break the ADS2 symmetries, so we should ask what are the symmetries of this problem, and then find the right Schwarzian and then quantize the Schwarzian. So to do this, we essentially take the limit where the black hole degenerates to an ADS2 cross S3 cross S5 vibration, and this is what the metric looks like. So it's just a little bit simpler than the full Gutkowski realm. And this is, again, an exact solution of type 2b supergravity. Okay, so when we take this metric and find what is the sort of space of large diffeomorphisms that act as redundancies on this solution, that's given by the sort of superconformal algebra or the Killing spinners and the Killing vectors. So we could compute the Killing spinners and the Killing vectors and find that they fill out an SU 1,1/1 superconformal algebra. So this is essentially the Schwarzian theory that this will, when I break this SU 1,1,1 and write down the effective field theory that describes the breaking of this group, that will be the ordinary Schwarzian plus a U1 gauge field, and that U1 here will end up being a combination of rotations along all the two angular directions on the S3 and the three angular directions on the S5. So, okay, some details, but this is some exact, these are exact symmetries of the extremal solution, and they're broken weakly by turning on a small temperature and a small deviation from BPS extremality. Okay, so are there questions on this so far? Maybe this is a good point to stop, because that's sort of, this completes the gravity side, and the last step will be to find the Schwarzian that computes the one loop determinants. So, and I'm just about done, and then I'll present the results. So are there questions on the gravity side, or? Okay, if not, then so then the final step is the idea of doing all of these manipulations with the saddle point approximation of the gravitational path integral is that we can put it in exactly the form where it looks like the n=2 super Schwarzian, and then use the previous results that we did it in much more detail by doing Kaluza-Klein reduction and identifying all the massive fields. But I'm kind of taking a shortcut in this talk, which is saying that in the end, the one loop determinants are going to be computed by the Schwarzian theory, which we know how to do those. So the idea is that the gravitational answer can end up being massaged into this particular form. This MSU111 is basically the specific heat of the black hole, and it's also the inverse of the Schwarzian coupling. This is the scale at which black hole thermodynamics is supposed to break down, and you can see that the idea is that there's some extremal R charge, some ground state energy, there's an extremal entropy, and then this is the linear in T correction to the entropy, which comes from the Schwarzian mode. But now, because I have some non-trivial gauge bundles, I have to sum over gauge bundles. So, and alpha again is the chemical potential. So I have some finite temperature beta, some finite chemical potential alpha, and then a sum over integers n, which determine these different bundles. So the last step is to find the one loop determinants. Okay, I said all this in words, so the rest of this part doesn't matter so much. Okay, so when we put it all together, we find that the final result for the partition function of, again, this is now, the claim is that at low enough temperatures, the partition function of the, say, ADS5 cross S5 with these particular boundary conditions such that the black hole is the dominant saddle. At low enough temperatures, the partition function will be given by this. And of course, in the full theory, there'll be an infinite tower of corrections on top of this, but this is sort of the exact result to the leading order in the inverse temperature. So this realizes some particular version of the n=2 Schwarzian theory that I didn't have time to discuss, but the point is that we computed some parameters of the quantum theory exactly using the 10D solution. Additionally, if we take this chemical potential and tune it to some particular value, here 1/2, this thing reproduces this function reproduces the superconformal index that was computed in n=4 Superyoung Mills by this matrix integral approach. So the idea is that our gravitational effective field theory, we can quantize it exactly and obtain the full partition function of the theory. Again, in the limit where the temperature is low enough where the Schwarzian results are valid. So we get the exact full partition function in this form, and a particular limit of it is the same as the superconformal index. So if you didn't have this Schwarzian EFT or the EFT of the gravitational theory, you wouldn't have known how to compute Z. You would have known how to compute the classical piece S star, but you wouldn't know how to compute Z. And the miracle is that we could compute Z exactly, but then when we tune the chemical potential to the BPS value, there's basically large cancellations in this sum here, and you're left with, again, essentially up to sort of an oscillating phase factor, you're left with e to the S star, and that's the large N superconformal index of n=4 Superyoung Mills. So this sort of shows that from the gravitational EFT, we can reproduce the exact results in field theory, at least at large N. Of course, there's going to be subleading corrections coming from D-branes and subleading saddles. So this is the large N answer that other people have obtained, and we've shown that it comes sort of in a, it comes from this two-dimensional gravity point of view. It also shows that one can see that this will also show that the index, the superconformal index, is the same as the degeneracy, and there's no guarantee that that's true. Okay, so this is a partition function. It's very nice. It's obviously a complicated function, but I want to turn it into the density of states to make contact with when we inverse Laplace transform and pass this some microcanonical description. This partition function will give us the density of states. This is common in statistical mechanics. So I'm just going to plot it for n=4 Superyoung Mills. So there are different charge sectors, different R charge sectors, essentially. So if we focus on the sector where there's supposed to be a BPS R charge, the spectrum, the density of states that we find, is something like this. So I've relabeled the mass of the black hole as the conformal dimension of an operator in n=4 Superyoung Mills. And so we can think of this as the density of states of n=4 Superyoung Mills when I've tuned the chemical potentials and the temperature very close to their BPS values. Again, this is attained via gravity and not via field theory. But so this is a prediction from gravity of what the field theory answer might be. And this is actually sort of a question I'd like to discuss with people when I finish this talk, which is just about done, which is, does anyone have any ideas for how to compute something like this in field theory? Remember that when supergravity is valid, that's at large N and large TÜV parameter. So that's, in n=4 Superyoung Mills, that's the limit in which the number of colors is going to infinity and the gauge coupling is going to infinity. So this is the extremely complicated, highly chaotic regime of n=4 Superyoung Mills. I won't bother explaining this plot. This 2D plot is sort of showing, because there's states of different R charge, there's essentially families of curves for each different R charge. Okay, so in a longer talk, I would give more details about that. But let me reproduce the plot, because we obtain this kind of density of states for all supersymmetric examples with at least n=2 supersymmetry. So there's a large class of supersymmetric black holes where when you apply this two-dimensional gravity analysis, you get this kind of spectrum. So let me just post this spectrum and sort of compare with what I was saying at the beginning of the talk about the tension between a microscopic microstate description versus gravity giving an average versus supersymmetric things are somehow integrable versus gravity is non-integrable. I kept saying all these things and it seems like a contrast. So I think this final picture, the goal will be to try to sort of summarize what we think is happening with these supersymmetric black holes. So if I have non-supersymmetric Einstein gravity and apply this Schwarzian analysis, the density of states is this sinh √E type curve. And this is essentially a curve that corresponds to a particular double-scaled random matrix integral. So the first comment is that the density of states is manifestly positive, which is good. But the second comment is that this density of states forms a continuum. This pink curve forms a continuum, which is in some sense bad. It doesn't correspond quite to an ordinary quantum system because the spectrum is continuous. But nevertheless, this is again what you would get from a random matrix theory. As the number of eigenvalues goes to infinity, you get a sort of continuous density of states. So we're seeing in the non-supersymmetric case, which again was obtained in 2 dimensions by some people, but the full 4-dimensional story was obtained by my collaborators and also with myself and others. So the punchline is that we get some kind of curve for a higher dimensional black hole at low temperatures, which has features of a random matrix theory. And what happens is that at large energies, it just agrees with the dotted curve, which is the Bekenstein-Hawking result. But as you tune temperatures lower and lower and lower, this phi r is this M gap scale. This is the scale where I said, roughly speaking, very general arguments from the 90s tell you that black hole thermodynamics has to fail. Well, right about at this gap scale, we find from this exact Schwarzschild result that the exact density of states begins to differ from the Bekenstein-Hawking density of states you would attain from Bekenstein-Hawking. And it gets worse and worse and worse as the energies get lower and lower and lower. So as I get closer and closer and closer to an exactly extremal black hole, the curve dips down. And one can show by looking at the entropy and the mass of this that correspond to the density of states. I didn't produce all the plots for this talk, but one can show that this fixes the problem with the Hawking quanta that I was saying, that once you get about to the scale where the Hawking quanta changes the energy by a large amount, actually the thermodynamics changes dramatically because, as I've tried to emphasize, this Schwarzian mode becomes strongly coupled at low temperatures. Nevertheless, it can be solved exactly, but it gives you very different answers from the semi-classical point of view. But finally, what I'll say is that, okay, in this non-supersymmetric case, very close to extremality down here at low energies, it really looks like essentially the density of states of the black holes is going to 0. So this suggests that even if there are small non-perturbative effects that go like e to the s naught that resolve individual microstates, because ultimately we think that black holes should be ordinary quantum systems. So even if there is some UV effects from string theory or from including all of the effective interactions of the gravitational theory, even if I include all of those that can resolve the states, it does look like in the non-supersymmetric case that the density of states is going to 0. So it's as if there are no exact non-extremal, there are no exact extremal non-supersymmetric black holes, if you trust the Schwarzian analysis. Which you might want to trust because it agrees with things semi-classically, and in the supersymmetric case, it agrees with the superconformal index. So without supersymmetry, we think that this is a better answer for the density of states of a supersymmetric black hole. Of course, this is not the exact result. It is the result that comes from the first correction, linear in the temperature, and it's also just an effective field theory. And in some ultraviolet models, such as string theory, we do believe that these individual states will be resolved. Of course, they'll be very densely packed, and it might be extremely hard to compute them because this black hole is seems to be subject to quantum chaos. But this is sort of giving the average density of states in the non-supersymmetric case. In the supersymmetric case, we find some very remarkable differences, which is, first of all, that the density of states actually goes to 0 at some non-zero entropy. So then essentially there's a gap where there's no states that come from this Schwarzian analysis. And then exactly at extremality, we get a very large, a delta function, in fact, that has a very large, that's weighted by e to the s naught. So we get a very large set of extremal black hole microstates, which is exactly equivalent to what you would have got from the Bekenstein-Hawking formula. So I think this is very bizarre, which is that, well, it's bizarre, but it's also consistent with what we know, because other people through the last 20 years have independently computed using supersymmetry, computed the superconformal index or supersymmetric index of some quantum mechanical theory dual to the black hole, and they got exactly this number. And they said, aha, it agrees with the Bekenstein-Hawking formula. Therefore, the Bekenstein-Hawking formula is true because in this, this supersymmetric case, we find a large number of degenerate states that is exactly equal to the area divided by, or e to the area divided by 4 g Newton. But what we're finding is that if we now sort of include the finite temperature corrections, So these black holes here are sort of non-supersymmetric black holes, but their charges are tuned, so they're very close to the supersymmetric ones. The claim is that these guys, once again, form a continuum, but now there's a gap between the non-supersymmetric black holes and the exact BPS ones. So the funny picture that's emerging is that perhaps people who computed the index in the past got the right answer for the wrong reason. And they may have incorrectly believed, I don't want to put words in their mouth, but they might have incorrectly believed that this dotted curve, which is sort of the semi-classical result, was always true. But now we think that maybe when one includes quantum corrections, which essentially come from the fact that the ADS2 is highly backreacting. And once I include the effect of all of the possible boundary wiggles, the boundary gravitons, once I include those effects, there's actually large cancellations, and the Bekenstein-Hawking formula becomes badly invalid at low energies. This gap scale here, this was also predicted in, say, the D1, D5 CFT by Maldacena and Susskind ages ago. Essentially, they used a free string winding argument to argue that there should be a gap, and they got this, again, 1 over phi r is, again, this MSU. I'm sorry, I changed notations, but phi r is like the heat capacity. So they also found this gap using sort of free string theory arguments, and we find it here again, just coming out of the gravitational path integral. I mean, we didn't know we were going to see these features until we Laplace transformed this crazy looking function. And then you find this surprising gap where this number is exactly what people got from some kind of free string theory analysis. So this is sort of saying that the gravitational path integral is reproducing the answers from ADS CFT and string theory, but by literally doing an integral over metrics in some sense. So I say, there's a discrete BPS spectrum from a gravity calculation, and then there's a gap, and then there's chaos regime. So that's the moral of the story. My claim is that for supersymmetric black holes, there seem to be some states in some sector of the theory that's sort of integrable and can be calculated exactly in gauge theory or maybe with some string theory type argument. And then there's also still some in the near BPS sector. There's some sort of highly degenerate, highly chaotic, densely spaced set of microstates, and gravity is giving some approximation to the ultimate UV theory that smooths out into this kind of curve. So okay, now is a great time to stop and ask if there are questions. Since I started maybe 10 minutes late, I don't think I'm too over time, but I have one or two discussion slides, but this is a great time to stop and ask if there are questions.
Okay, thanks. Questions?
I have one question. Maybe two questions. So one is here when you consider the near horizon limit, probably you consider only the short gravity, right? Pure gravity.
Sorry, so once I take the near horizon limit, what?
You consider only the maybe I have it. Yeah. So you just consider the pure gravity short jet. So you don't have to consider this like a 2D gravity coupled method because you only consider the reading large n and it's leading, or is there some other region?
Right. So the question is, why didn't I consider essentially JT gravity? So JT gravity is equivalent to the Schwarzschild because it's sort of a topological theory and it reduces to the boundary term. And you're asking, why didn't I consider JT gravity coupled to matter? Because I'm reducing from 10D, there's a billion Kaluza-Klein fields, massive and potentially massless fields. Why did I somehow only keep the sort of the leading action for the massless fields? The argument is not made precise in this ADS5 cross S5 case, I have to admit, but in the 4-dimensional flat space black holes, we have some more precise argument for this, which is that if I do include the contributions from extra matter fields, if they're massive, when I integrate them out, they will produce some log area corrections, LSN, but they don't produce sort of temperature dependence. So the idea here was that I want to look at the things that essentially are relevant at low enough temperatures. And the miracle of the fields that show up in JT gravity and then the Schwarzian description is that by doing sort of a field redefinition, or by redefining the length of the time circle, I can pull the temperature out of the Lagrangian, and so that the temperature sort of becomes part of the coupling constant. Okay, that's a little mysterious sounding, but what I mean is that the length of this boundary curve can be seen for the Schwarzian derivative to set the scale of the interaction, and it's the JT gravity fields and the associated Schwarzian mode. Those things grow in their contribution at low temperatures. So as the temperature gets lower and lower and lower, the Schwarzian becomes more and more strongly coupled. So all the other matter fields, as long as they don't have temperature dependence when I do their path integral, they'll always be subleading because they don't grow with temperature. That's not to say that this argument will always be true. It appears to be true in some examples where you can sort of explicitly do the one loop determinants and find that they don't have temperature dependence. So they're subleading compared to the Schwarzian mode. Yeah, but certainly a more careful analysis would involve actually doing the most honest 10D Kaluza-Klein reduction, which sounds very hard. I don't think anyone has even done Sen's logarithmic entropy function for ADS5 cross S5 black holes. But the most honest thing to do would be to keep the entire Kaluza-Klein ansatz and do those integrals one at a time. And I believe that ultimately you would find that if you only care about the low temperature behavior, the Schwarzian mode is the dominant correction. But of course, one could systematically compute the corrections to that. But JT is the leading part of the answer. That's sort of the argument. Yeah.
Another question is here you consider n equal 2 case, or is there can you consider a higher supersymmetry case?
Yeah. So there was a whole different talk that could have happened in which I consider the black holes in flat space 4D n equals 2 supergravity, for instance. So okay, I'm scrolling all the way back here. Sorry, let me just hit escape and right. Oh, here we go, right here. So this was the case that we actually analyzed first before these ADS5 black holes. So essentially the Reisner-Nordstrom black holes in n equals 2 supergravity. So 4D, and I know this counting of Susie is different. So in 4 dimensions, if I have a 4D n equals 2 theory, or I could also have a 4D n equals 8 theory, and consider Reisner-Nordstrom black holes in those supergravity theories, the near horizon JT theory will have n equals 4 sort of 2D or 1D n equals 4 supersymmetry, and that's associated with this PSU 112 symmetry of the near horizon region. So this is the largest amount of supersymmetry that we found in any example, and largest amount of 1D supersymmetry we found. I don't know of any gravity solutions that have a 2-dimensional throat region that has more supersymmetry. So let me give it a specific example. Let's say I took D0 branes in type 2A string theory. And I just took D0 branes. So there's an S8 horizon, and this theory has 16 supercharges. So it looks like a maximally supersymmetric quantum mechanics theory if I look at the world volume of coincident D0 branes. But the problem is that on the gravity side, as I take the number of D0 branes to be large, there's large back reaction, and the gravity solution I get actually doesn't have an ADS2 region. Essentially, the horizon area goes to 0 as I approach the extremality. So all of these examples that we considered where the Schwarzian description is valid, that's where I have a large horizon area. So it may be that there are Schwarzians with more than n equals 4 supersymmetry, but I don't know of any gravity examples where they're realized, because it seems like, roughly speaking, you need multi-charge black holes in string theory to have large black holes rather than small black holes. And the Schwarzian arguments I gave for why that's the only thing that's relevant, that's only true for large black holes. I don't know, well, at least I don't know if it's true for small black holes. So if there are supersymmetric
theory, you can do that. I don't know this geometric meaning, but using the BF theory, you choosing some other group, and I think it's possible. I remember this Grumiller's paper.
Yes, indeed.
Yes. But this theory maybe black hole is some different from the n equal 4 or n equal 2.
Right. So the Grumiller paper does indeed have OSP 2/n for any n, and it appears that you can write down a JT gravity theory, and perhaps also some theory with n equals whatever super reparameterizations. So in two-dimensional gravity, it seems that I can formally write down models that have that structure from the Grimm-Miller paper, which was super helpful to us, by the way. I don't know if I actually cited them. I'm embarrassed if I didn't, because their paper was super helpful for us. Again, from the bulk point of view, I don't know if there's a bulk solution that realizes these OSP 2/n's, or at least a bulk solution that realizes those where the arguments that JT gravity is important are still true. So I would love, yeah, if anyone has ideas on it, I'd love to know. Yeah, these ones have large semi-classical smooth horizons. So that's why this n = 4 was the most that we tried explicitly. Are there other corrections? I had a couple extra slides here at the end that I didn't have to go through. We also included the stringy corrections to the Schwarzschild. So we include the leading corrections to type 2b supergravity, essentially the leading alpha prime corrections. And what that does is it changes the gap scale of the Schwarzschild, but doesn't change essentially the shape. So it gives you an alpha prime dependent shift to the coupling. So, eventually, if you started including more and more and more stringy corrections, the geometry becomes more and more stringy, and maybe at some point JT gravity is not valid. But the leading correction we can take into account, and it basically just shifts some of the numbers by an alpha prime dependent amount. But at least in principle, we could start to imagine interpolating to the weakly coupled, or the regime where the dual gauge theory is weakly coupled. So this was nice that in some sense, even a little bit of stringiness doesn't change the argument. And it changes answers in a systematic way we can control. And okay, there was a discussion slide, but I think we're already discussing, so I don't need this. I'll leave it on this slide. Are there any further questions?
Matthew, since it's quite over the regular schedule.
Sorry, over the what?
Yeah, we were getting too late. So
oh, we're going overtime. I see. Yeah. Okay.
So there is no other question. Let's conclude. Yes, and let's thank Matthew.